Okay, let me introduce the next talk. The next talk is the Graphitron, a domain-specific language for FPGA-based graph processing accelerator generation. So presenter will be Xinmiao from Institute of SKLP. Okay, you can start.
Thanks for your introduction. Good afternoon, everyone. My name is Zhang Xinmiao, and I'm a PhD student from Institute of Computing Technology, Chinese Academy of Sciences. Today, I'm happy to present our work, Graphitron, a domain-specific language for FPGA-based graph processing accelerator generation. This work is a collaboration with Hong Kong University of Science and Technology, Guangzhou. Now let's get started. Here's the outline of my talk. I will start with background and motivation. Then I will introduce the design of Graphitron and describe the workflow of its compiler. Then finally, I will present the evaluation results and end with our conclusion. Graphs are everywhere. Since Liang and Euler used the graph to solve the 7 bridges problem, graph has demonstrated exceptional expressive power and is widely used across a broad range of disciplines, including social network, finance, transportation, and knowledge graph. As a result, graph processing has become a fundamental building block in many large-scale data processing systems. Graph algorithms present 2 key challenges. First, they involve a huge number of irregular memory accesses and have a poor locality. On CPUs, this will cause frequent cache misses, resulting in low cache efficiency. Second, because of the power load distribution of the graph, there is severe workload imbalance. On GPU, this will lead to warp divergence, where threads in the same warp follow different control paths and serialize execution. As a result, general-purpose computing engines suffer from low hardware utilization and poor energy efficiency when running graph-related workloads. FPGAs offers a promising alternative. They support custom memory and execution paths, have high parallelism with low power consumption, and provide fine-grained scheduling. These traits make them ideal for graph processing on the edge side, such as smart camera, V2X network, and industrial IoT. For example, in V2X systems, vehicle-to-intersection communication forms a road graph where local edge computation helps with the cooperative path planning. However, despite of the advantage of FPGAs, given the diversity of graph algorithms, designing efficient accelerator remains very challenging, particularly for those without expertise in FPGAs. Many FPGA-based graph processing frameworks have been proposed to lower the programming barrier by providing easy-to-use interfaces. These frameworks typically rely on a pre-built accelerator template or hardware overlays that incorporate various hardware optimizations for generating the accelerator. However, this tight coupling of programming models, processing paradigms, and accelerator architecture can limit the flexibility and lead to suboptimal performance of the generated accelerator. Firstly, only algorithm capable with the provided programming interfaces can be expressed in the framework. It will limit the expression scope of the algorithm. Moreover, the pre-built accelerator template adopts a fixed processing paradigm. For example, edge-centric or vertex-centric ECP or VCP to integrate the specialized hardware optimization. These approaches may perform poorly for some of the algorithms. For example, ECP is effective for algorithms such as PageRank, where all vertices are active. However, it struggles with BFS, which only activates a subset of vertices, resulting in considerable redundancy. This limitation underscores the need for a more flexible method of generating FPGA-based graph processing accelerators. In the CPU or GPU domains, Graphite is a well-known DSL for parallel graph processing, which decouples graph algorithm descriptions from their optimization strategies with easy-to-use algorithm and scheduling language. The algorithm language makes it flexible to describe the algorithm, and the scheduling language expands the optimization space by manually indicating the optimization strategy. Inspired by it, we seek to bring this idea to FPGA domain, enabling flexible algorithm expression while ensuring efficient hardware generation, and finally make efficient FPGA-based graph accelerators available to everyone. However, the challenge in designing such a DSL lies in balancing abstraction with the customization, which means on one side, different from Graphite, which exposes the optimization to the users, our DSL should allow users to describe algorithm without dealing with any low-level FPGA details, especially considering that users may not be familiar with FPGA at all. On the other hand, removing those manual optimization requires the compiler to infer and apply hardware optimization automatically to the generated accelerator, which is challenging given the diverse computation and memory access patterns in graph algorithms. Next, I will introduce our design of Graphitron. This figure illustrates the development workflow of Graphitron. From a high-level user's perspective, they can flexibly describe the algorithm by customizing operators to vertices and edges in the graph, and then orchestrating their workflow through writing the Graphitron code. During programming, users do not need to specify any FPGA-based optimization. Then the compiler of Graphitron produces HLS-based FPGA accelerators. The front end ensures the code correctness by grammar checks and resolving ambiguous issues encountered in many FPGA-based graph processing frameworks. Subsequently, the middle end conducts semantic analysis and infers suitable hardware optimizations, annotating these optimizations as text in the intermediate representation. In the backend, Graphitron integrates this optimization on the accelerator kernels to generate graph processing accelerators. Finally, for system integration, the compiler generates the host program, which is responsible for graph partitioning, workflow control, and FPGA device management. Let's start with the DSL design. The DSL is an object-oriented programming language. It abstracts the vertex and edges as data types to instantiate the graph objects. We take Graphitron code for BFS as an example. Firstly, user should specify the graph file and construct the vertex set and edge set as graph objects at the beginning of the code, and define all the data structures, which is also known as properties related to these objects. Secondly, user can define some operators for these objects to describe the procedure of graph algorithms. Finally, user can describe the whole graph algorithm workflow by orchestrating these predefined operators through calling the provided API. In this way, Graphitron can naturally support VCP, ECP, or their hybrid processing paradigms by customizing operators to the edges and the vertices. For example, Graphitron code for BFS with hybrid paradigm is shown in the listing. It implements seamless transition between the VCP and ECP based on the runtime frontier size. From the compiler side, the front end constructs an abstract syntax tree and generates the front-end IR. Our front-end involves a self-developed lexer and parser tailored for handling graph-centric object abstraction, such as vertex, edge, and their property, thus directly mapping these concepts without excessive pragma or hints. The middle end of the compiler maps these concepts to the target FPGA and adds some hardware optimization tags. In detail, the compiler allocates the appropriate memory space for these objects, then automatically assigns memory units and their channel ID to the objects, enabling the FPGA to efficiently allocate the memory and manage the pointers for transferring data to hardware kernels. Besides, the middle end infers and adds some hardware optimization tags to the operators, including the memory optimizations for graph properties and the parallel and the pipelining optimization for the operator. The parallel tag is added to the operator automatically. It will use to unroll loops to maximize the data parallelism. To determine the optimal unroll factor, the compiler sets the parameter as the number of memory channels where the corresponding object is allocated. For the pipeline tags, we rely on the HLS tools to automatically determine the minimal feasible initial interval for instruction level parallelism. Besides, Graphitron incorporates optimizations to graph properties to improve their access efficiency. The burst read and write module has much higher sequential bandwidth than the normal read or write to the memory, so we utilize this module to read or write properties. However, the properties related to different objects exhibit distinct access patterns. Edge-related properties are typically accessed sequentially, whereas vertex-related properties involve a lot of random accesses. Consequently, we adopt a tailored memory access optimization based on the differences. For the edge properties, we simply utilize the burst read or write to maximize the sequential bandwidth. For vertex-related properties, we need to fully utilize the loaded data by the burst read or write. So we allocate a dedicated cache module with FPGA's Ultra RAM to enhance the data reuse. Additionally, for vertex properties holding random writes, we implement a shuffling module before burst writing to convert the random writes into the sequential writes and facilitate conflict-free operations for higher bandwidth, further improving the memory throughput. Finally, this figure illustrates the overall background framework of the generated kernel by the backend. Instead of relying on the built-in accelerator template, it employs a generic architecture comprising basic modules designed to accommodate a broad spectrum of algorithms. For each operators, the properties of related graph object are first streamed from FPGA memory into the cache module. Then the vertex or edge process module perform the user-defined function to generate the update streams. If the output is not marked as shuffling, the update stream is directly written back to the memory. Conversely, the stream is further routed to the stream duplicate module, and it is duplicated, sliced, and distributed across different PE. In each PE, the shuffling model reorganizes the update stream and filters out the unnecessary update. Subsequently, conflicts are resolved by the REW module, and the redundant updates are aggregated by the reduce module. The resulting updates, which are sequential, are then stored into the cache. Finally, the updated properties are streamingly written back to the FPGA memory. Finally, here comes our evaluation. We implemented Graphitron on Xilinx LVU 280 FPGA. We tested 6 graph datasets from different categories. We tested 5 different graph algorithms, including 3 graph traversal algorithms, BFS, SSP, PageRank, and 2 emerging algorithms, personalized PageRank and graph attention. We compare against standard GP, a state-of-art FPGA graph framework, which is a representative benchmark for the performance, and a naive HLS implementation, which is a benchmark for flexibility. As we evaluated, both Graphitron and standard GP significantly outperformed the naive HLS implementation, primarily due to their integrated optimizations. Furthermore, Graphitron consistently achieved better performance than standard GP for BFS and SSP. The reason is that Graphitron enables users to implement the accelerator with hybrid kernels of both VCP and ECP paradigm, reducing a number of redundant edge traversals. However, its performance in PageRank is slightly lower compared to standard GP. This gap arises because standard GP only supports returning the cumulative sum of differences between old and new PageRank values. In contrast, Graphitron develops the flexibility to individually record these differences, so introducing some more overhead. The most significant performance improvement stems from the memory access optimization. We designate Graphitron variants that individually integrate burst rate, shuffling, or caching, respectively. And we show the result. The result indicates that incorporating only a single memory access optimization yields limited performance gains. This occurs because optimizing only one memory access pattern leaves other a bottleneck. As for flexibility, due to the reliance on a fixed programming interface, standard GP cannot support algorithms such as PPR and graph attention. In contrast, Graphitron achieves average speedup of 71 and 240 times over the naive HLS implementation, respectively, demonstrating a strong performance combined with high flexibility. As for the design productivity, when writing a new algorithm, standard GP demands modification across at least 5 different files, while Graphitron enables users to implement a graph algorithm with fewer than 100 line codes. Besides, standard GP's configurations often require extensive FPGA-based expertise, and Graphitron empower even inexperienced users to efficiently customize the graph acceleration. To summarize, we propose Graphitron, a DSL for FPGA-based graph processing. It enables flexible, high-level graph algorithm and compiles to optimized hardware designs. Thank you for your listening. I'm happy to answer your questions.
Okay, thank you for the great talk. So, because of the time limitations, we will just get the only one question. Any questions so far? Okay, so I have actually several questions, but only one question will be like this. Okay. Oh, sorry. There are 2 different FPGA companies for the Xilinx and the Altera, right? Okay. So yeah. So are your optimization techniques independent to the hardware vendors or not? So which means that if you target another different FPGA from the Intel Altera devices, okay, so will you share some of your optimization techniques or not?
So now I just focus on one vendor, just.
But in general.
Yes, but I think If you want to target another platform from different vendors, you can just modify the backend of the FPGA, I think.
Yeah, that is my question. So which means that do you have any specific optimization in the backend, considering the backend hardware or not?
Yes, I think some of the automations are special for.
Okay, thanks.
Okay, thank you.
Okay, thank you again. Okay, let's move to the next talk.